Thank you very much, Alexandros, for this. Even the subject is rather precise, very excited presentation. We had now two presentations that gave you, first of all, a broad overview of the project itself, CreepUT, by Marco, and now the importance of Creep itself for the industry, the power industry, made by Alexandros. I would like here to understand that myself, being a complete novice on the issue, thanks to Marcos and Alexandros' presentations, I understood clearly not only the importance of Creep for the industry, but as well the importance of these instruments that we had here today for the type 4 Creep damage, and because of these explanations. So now, without further ado, we're going to proceed with Channa's background on R&D towards the CreepUT project itself. So as you see, we go from the general to the more specific topics. And now, may I invite Channa to take the floor and make this presentation for us.
Thank you, and good morning, everyone. So just to give some information about myself, I'm working in this consortium representing TWI, and I'm going to today talk about the work that has been done in TWI, as well as in this project, as well as related previous projects, and how we got to where we are today. My role in TWI is to manage R&D teams, as well as look after the core research program, which is an internal TWI program for fundamental research. So TWI was approached in 2010 by two companies, RWE and Scottish and Southern Energy, to look into some failures that had taken place at that time, and try and develop a inspection solution for this. And I have here a image of the component that we worked on, which is a branch weld, which had been in service for some considerable amount of hours. It was made in of the kind of grades that Alex has been talking to us about. And what we had was a configuration of wells, which were termed set-on wells, which went around the nozzle and presented some problems geometrically for the inspection, which we had to solve before we can address the actual creep problem that was found. So here you can see how the geometry of the well changes around the branch, depending on whether you're at the 0 degree and 180 degree, or the 90 and the 270 degrees, as well as internal radii and changes in material conditions. This was something that we had to first of all address in order to be able to find type 4 creep damage. So this is an image of an actual crack that was found. It was not the component that we were given to work on, but it was another component from the same header system, and you can clearly see that there is a cracking that has appeared on the surface. So the client was provided. So this is a cross-sectional view, and so you can see different zones in which were then classed through replication to contain different levels of damage, and these were the zones that we were looking to find the damage in as well, in other sister headers and components from that system. So the challenge was an inspection challenge, and the aim was to find the early emergence of these of this kind of voiding that is representative of the damage in its early stages, in the secondary stage. So when the client was given a report, they were given this report. So you had clearly a surface breaking flow about 5 to 7 millimeters in depth, and clearly it was not deemed to be critical, this particular flow, because it hadn't traveled very far, But as Alex pointed out, the problem is that very often it starts from the inside and moves outwards. And so there is the possibility that it could travel to lead to a full fracture before there is any evidence of it on the surface. So methods such as magnetic particle inspection, dye penetrant inspection, replication, and so on are relatively insensitive to these type of damages until it arrives near the surface. So the aim was to try and detect this kind of damage before it turns into a crack and while it's subsurface. So you've seen this image a few times now. So what we developed, and that project led to something called CREEP, which I'll talk about in a while, found that we were able to detect the damage at this level, which is microcracking, which the client considers to be still a little bit too late. And so the end of that project, the briefing back to us was that, okay, that's fine, but we really need to go even earlier. And so that's where creep test worked. That was the level at which creep test was working. And potentially in the future, we are now thinking of even earlier stage damage based on the progress that we've been making. So the CREEP project, as stated here, these tables are a bit outdated now, but this is a slide from that project earlier on. And we set out to solve an inspection problem and found examples of damage at level 4. So the client gave us a specimen in which we weren't successful in finding level at 3A3B, so we weren't, it was not possible to prove whether it was possible to detect it or not at that level, but we certainly did find things at the level 4. And so the CREEP project, which was a UK Technology Strategy Board funded project with RWE and SSE, demonstrated that this was possible. But the CREEP test project had to work on 3A and 3B, which required some changes in the way we approach the problem. Some background work done at the time also indicated, so this is kind of literature review and capability analysis done, and if you see in 2010, exactly when we started this program of work, a paper was published from Imperial College, which indicated that the backscatter method has required more research, but has the possibility to find localized damage subsurface. If you look at the rest of these kind of methods that could potentially have been applied, many of them are lacking what was necessary. So we really had only this one to consider as both likely to lead to success, as well as being open for further work, whereas some methods, like for instance ultrasonic attenuation, had been shown to be quite poor, as well as being bulk and volumetric. So it's not a method that will be very sensitive to localized damage such as type 4. So that was the approach that we took. So the Cree project, which was funded for a very rapid turnaround, a 1-year feasibility, led to the development of this scanning system and the use of a 2-dimensional phased array probe. So this is a 256 element phased array probe that was able to steer the beam in the 2 planes in order to deal with the complex shape weld geometry that I talked about earlier. So that project essentially led to some positives, which was that it was possible to deal with nozzles, and from that on, that stream of work is a separate approach that led to some other developments. But the negative was that we weren't able to prove that we were able to find anything which is earlier stage than level 4, stage 4. And that was primarily, at least at the time, limited by the frequencies that the phased array probes could achieve that were commercially available, which was restricted to less than 20 megahertz. So those were kind of like the findings and key lessons learned. And when we did some theoretical assessment at that time, similar to what Marco showed, what you have here is with reference to a standard 3 millimeter sideral hole, which is the reference signal. If you look at diffraction from a crack-like flow, you need to have a system that will be able to give you signal-to-noise performance good enough for something that is 18 decibels below that crack. If you're looking for a 1 millimeter spherical void, such as porosity, then you're looking at 15 decibels down from that. But you can see that if you're looking for a 0.1 millimeter spherical void, which is already 100 micron, which is even larger than the kind of voids, individual voids that you find in a metallurgical structure, you're looking at double what you need for a crack. So that gives you a very good approximate idea of the level of sensitivity that the system requires in order to be able to find creep damage. So we had a large number of specimens from actual plants, and this is an example of a header. So this is at the top of the boiler stack, experiencing quite heavy temperature fluctuations, as well as being made up of P91 and the kind of grades of steel that Alex talked about. And they were known also to suffer at these branching wells. So this was provided by SSC, and it was taken out of Ferry Bridge. And you can see areas where replication had been done by the power company at routine maintenance to try and establish if any surface flows were taking place. So this was taken out during a routine outage and sent to TWI for assessment. And so using similar methods, but and using high frequency probe as high as we could get at the time, we tried to find that kind of flows. To establish whether any flows did exist in those branch wells, and the results were not conclusive. We did section the branch, and there was creep damage for sure. There was absolutely general creep damage, as you would expect, over the entire metal, but there was no evidence that we could find of localized damage. But at the time, we were also not confident of our technique, so it was not possible to conclude effectively. So in 2013, we started the Creep test project, which involved KTU, Applied, and Innertech, and also SSE at the time. So what we then decided to do, based on the experience of the Creep project previously, was to go back to the fundamentals and consider what we need to do from the point of view of the flow, rather than from what we have available in terms of equipment. So it was clear from the outset that we needed to go back to creating an equipment specifically for this application. In addition, based on our inspections of the headers from SSC, we wanted to come up with something that could be applied in the field. So the first problem we faced was specimens. So up until that point, we had been receiving specimens from power plants, things that had been in service, which the power plants obviously were rightly concerned about for creep damage, but there was no obvious evidence of actual type 4 damage. Now, it would have been possible to search for this type 4 damage, and the only way to really do it is to section it. But of course, once you section it, you destroy the specimen at the same time. So it was not really an approach that was going to be viable. First of all, to section these components, like the ones you saw earlier from the header, takes a lot of money. And then even after that, it's no guarantee that you will actually get any subsurface damage, which you can then use to do your work on. And so we had to create specimens. Now we'll talk about specimens later. And the other one was frequency, because frequency has a lot of effect, as Marco said, on the fundamental resolution, the temporal resolution for the damage. But also it has a lot of influence on the practical implementation side, because higher the frequency, the more sensitive it becomes to surface condition of your component, even before you get a chance to look at what is underneath the surface. So we knew that we were going to have a challenge with frequency. And then the third approach was that we knew that we had to work on the signal processing side, because the amplitude-based detection that is often used in ultrasonic testing was not going to be sufficient, because amplitude is affected by noise, and noise is a parasitic quantity that we have to deal with when we are trying to find flows. So those three were the key aspects of any research and development project for this application. So coming back to the frequency spectrum, the CreepUT using phased array, and phased array has many advantages such as focusing, steering, two-dimensional probes, dealing with complex geometries and so on, but it was limited to this level, around 18 megahertz at the time. There are some improvements on this, but it's not industrially robust system. But the CreepTest project then focused on single element probes, and that's where we are now with the CreepUT project as well, in order to reach into this area of the spectrum. And this is some theoretical work done in KTU during the CreepTest project, which also shows and supports the previous evaluation that when you're looking at something that is about 0.1 millimeter diameter, you're looking at the sensitivity levels which are quite tight at 10 megahertz. If you wanted to go even higher and become even more sensitive, so you can see for a 0.1 millimeter target, you can achieve better, you can detect better with better signals here, around minus 15 dB, if you use 50 megahertz. But 50 megahertz is not very easy to implement because of surface condition. It's very difficult to control. You have attenuation levels become excessive so that you can't really look very deep underneath the steel. And then the electronics as well becomes much more difficult to condition. So we were limited to this range. And we also decided in consultation with SSE at the time that we should look at butt welded components which are representative of the main streamline piping system, because they experience very high temperatures that approach supercritical levels, as well as having a geometry that we could deal with in the beginning without having the issues of the branch wells of a header system or a cooling system. So that's the component that was focused on, and that's an exact diagram of a pipeline system inside Ferry Bridge. And the idea was to have two operators. One would be working close to the component with a scanner at less than 10 kilogram. Another operator working greater than up to 10 meters away with a customized pulsar receiver unit, as well as a user interface for the operation. And a lot of the things that we now have focused on in the CreepUT, such as the user interface of the software having to be user-friendly, all came out of these kind of early exploration of how to configure this side. And what we also wanted to do was to tag our inspection procedures to the replication procedures, because at 25 to 30 odd megahertz, we needed to achieve surface conditions which were basically being applied by field metallography operators. So we can just go back behind them and then implement the UT. So the idea was that the replication will look for surface indications, and then we will support that with subsurface indications using a UT system. So this is a prototype scanner that we developed, which was essentially an R&D scanner, and it was expected to be as such. It was not really configured for site work, though it could have been taken on site. This is a piece of steel that was provided by SSE, into which we put some targets, some calibration targets for setting up the scanner. And you can see the kind of rough dimensions, and it was quite a large, chunky scanner, but able to operate two probes in order so that we can explore different configurations. And this was the prototype system that we ended up with at the end of the project, and it has all the components which are now currently in the CreepUT system, which is the scanner, again that scanner, but now miniaturized and better conditioned for power plant environment. We have the water feed unit, which is an automated system at the time, able to provide the water as a constant feed, because you needed to have that quality of signals as a primary requirement. And then you had customized electronics, as well as motor controller, and then some software that was built by a partner at the time who is no longer in this project, NTUA. Then we were provided with the contacts from SSC, an extract from a component in which an actual type flow crack was found, and you can see that ahead of the crack tip, you had regions of much smaller. So that's a scale of 500 microns. You can see things that are basically approaching the levels of damage, which at the very tip would be classed somewhere near level 2. So this was then used as the primary object for validation, and that block is underneath this scanner, and we scanned that block with the aim of trying to detect signals from that crack tip. And for the specimens, so TWI then invested quite a lot of effort into trying to generate specimens which did not come from power plants. And so we used essentially standard creep test machines, which are used to test components to failure and establish their creep rupture strengths, and then rig them in various ways to try and interrupt the tests during the point at which the specimens go from the secondary to the tertiary stage. So that's it's a relatively fast region, and we went through multiple iterations to try and stop the specimens before they went too far. And the kind of specimens we also looked at were these kinds of specimens which derive from the standardized creep test specimens, which are essentially circular. But what we have is essentially specimens that were flat, so that the UT calibration and testing aspects could be implemented more easily. So there were lots of issues, like, for instance, the need to create this radius, because otherwise you have areas of sharp stress risers. And so what would happen is you load the specimen, and then in the primary stage it would fast fracture, because the stress raises were too high. And so, that's a 4.5 millimeter gauge length, which is not very strong for the levels of stresses that we were imparting. So currently, as part of that program, but also currently as part of the CreepUT, we've moved from kind of these static loading creep specimen testers to fatigue loading creep testing specimens. So fatigue loading gives you the opportunity to do something faster. So for instance, to get the average time to get any results from this can range from 2,000 to 4,000 hours, because you need to move the creep slowly through the secondary phase. But we have, as part of the core research program, work ongoing to seeing if we can accelerate that process using the fatigue method, because fatigue will add stress, but you can operate at stresses which are much lower than yield, and it can be achieved possibly in much quicker. So that's kind of ongoing work, but the whole specimen generation projects are related to the core research program, as well as related microstructural damage mechanisms such as HDHA. So this is quite a large part of the work that TW has been involved in as part of this project, as well as others. And here is an example of a weld. In this case, it's an electron beam weld, which is one way of introducing a nice heat-affected zone, a controllable heat-affected zone. Whereas in arc welds, as Alex pointed out, when you're applying multiple beads, they temper the previous beads, and so you get up with a non-uniform microstructure. Whereas when you're using an electron beam weld, electron beam is a very high energy process, and they will apply a beam very quickly and then leave you a very nice uniform heat-affected zone. And so we found that this kind of welding process gives rise to much better kind of conditions. So here you can see actually something that is fairly late stage damage, whereas on this side you can see damage which is much earlier stage. And so that's that's a fairly representative set of specimens that can then be used for the implementation of or checking or validation of creep testing systems, UT, but also other things. For instance, X-ray computer tomography has been implemented using these kind of specimens. So it's an important aspect of any system, and in the creep test project, we were able to then find a way of validating the creep test system using a specimen which had cracking at 1.4 millimeters away from the well boundary. And this was inspected in this direction. So it inspects in the optimum direction to be able to detect this, but the surface area, so the wavefront meets a level of damage which is very close to sub 50 micron level change in the metal. So it's in the 3A 3B region when you inspect in that direction. And when we look even closer, you can see the damage at various different levels. So 50 microns here, and then 300 microns there. So it was possible to get a range of damage in specimens. And when you look at the data, so you have, this is data collected from the CreepUT by KTU, and you put the data adjacent to the damage, and then using a processed parameter, it was clear that the signal to noise here is easy to interpret that there is a microstructural change at that position in the metal. And so that's essentially the premise for the Creep test system. And during the Creep test project, we also SSC started providing, that's Ferry Bridge C at the background, which is a very important power station for our work. And they started providing specimens which had been in service, and you can see a number of specimens in the holding yard, which then come to TWI to be replicated across the weld. And then using the Creep test system, in this case, we were able to see as we move, so x equals 3, 4, 7, 11. So as we move into the weld from the parent, you can see increasing changes. For instance, that is the HAZ region. You can see increased levels of damage in the HAZ, which we subsequently showed to be related to type 4 creep. And as you go into the weld metal, you have increased levels, but not as increased as that. So it was then clear that we could actually detect creep, and we were confident that creep at 3A 3B can be detected. So what that left us was essentially the problem of field implementation. And these are some additional images of components that we looked at during CreepUT from Ferry Bridge as well, trying to find areas of damage. So in 2017, we founded the CreepUT project, and its primary goal was not really to the development of the technique was there. It was to begin trying to bring that to site. And so this is work done on TWI's side by an initial version of the scanner to be implemented in the field. It was sub half a kilogram, which is the good point, plus point. But when we went to Cardia during the project and found the condition of the dust and the particulate matter, it was quite clear that these moving mechanisms were going to be affected. So based on that visit, we revised it to the current version of the system, which is essentially enclosed. And we are now working to change to achieve IP65 or 67 rating on this scanner by changing the way it's been designed, but the essential form of the scanner remains the same. So you have a replaceable feet, which will configure to different pipe-like components. You have a scanner box which has the motors and encoders inside. Well, in this case, no encoders, but encases it to prevent the ingress of dust and achieve robust operation. And what it has essentially is a shaft that comes out, onto which there is a probe holder connection, which Inetec worked on. And then this little square represents the replication area over which we scan to assess the subsurface creep condition. So that's essentially the instrument. And here you can see the instrument working on one of our field trials, and you can see an operator at the back. And similarly, here's another Yuritsa over there, looking very serious. And you have the scanner with the probe, and then the couple and feeding pipes there as well. So to conclude, it's been an 8-year journey for TWI, and for the CreepUT project, it's been 2 years up till this point. And we are at a position where we are able to go to power plants and industrial inspection service providers and say, okay, we are quite close now. We are quite close to produce a system that can be implemented in the field. And it is capable of detecting early type 4 damage, and what remains now is really building confidence with power plant operators like PPC, SSE, RWE, by taking the system to a place where it can be tested over a long-term period without the pressure of results, because I think the inspection challenge here is very, very, very hard. And so you can't expect these systems to be commissioned and qualified for general use very quickly. But this process, this 8-year process, has gone from an initial look failure, then a second look with a better appreciation of the fundamental requirements, and then a third approach now with the CreepUT, which has addressed the other the aspects, which are the important practical aspects. And so we are at that junction where we are able to bring the system to a power plant and begin to start exploring it, but it will still take some time, and these kind of events are really to bring the awareness of the system in the general market, so that people will give us the opportunity to then to take it out and explore it. But as I'm sure a lot of the people here know, that the opportunity, the size of the market for this system is big. But it's not just type 4 creep damage, it's a lot of other microstructural damage. For instance, HDHA and other kinds of things that lead to changes in the microstructure, which can be addressed with this system. And so it's a big market. I think, thank you very much.